You are able to see the screen? Okay.
Also there, sir.
Yeah, I was told. Okay. Okay. Is it on? Or I should switch it on. Yeah. Good. You have heard the introduction. Don't worry about it. I'm a teacher, was working at IIT Madras in the Department of Physics. So I'm very happy to be with you today to give you a glimpse of the fundamentals of or basics of quantum mechanics. This is an odd subject for the simple reason people talk about quantum computing so large, we don't know what we are talking about. So in the next 80 minutes, I'll try to give you the history of quantum mechanics, which is already about 125 years old. And if I say you are most familiar with quantum mechanics, you will agree with me. For example, if somebody asks you, do you have a brain? Do you have a brain? Show me. Can you show that? Can you show your brain to me? Can anybody show their brain to me? I can show my brain to you. If I just take an MRI, MRI will give you the image of the brain. It's only one example. Now you may ask me how quantum mechanics is related to MRI. The story goes back to 1932. Purcell has discovered quantization of angular momentum by the electrons. Quantization of angular momentum. 1942, he got the Nobel Prize. 1969, the concept of tomography. Tomography is a part of mathematics, which means that you have a big function, you can slice it to smaller functions, look at the smaller functions, and you can put it back together. It's almost like you take a potato, make it into small chips, look at the inside of the potato, whether it is good or bad. Then you put all the slices back, close it down. This is what tomography means. To understand the slices, it requires a lot of computation. So 1970, we got the personal computers. So the combination of quantization of angular momentum, the discovery of tomography in mathematics, and the coming up of personal computers, all the three brought together, and this bringing them together gave you the MRI. So now you cannot say that quantum mechanics is different and I am different. How many of you are seeing the lasers? This is a laser pointer. These lasers work with quantum mechanics, which we say the population inversion in the band structures of the electrons, which will give you the lasing action. So quantum mechanics in this 125 years has given us practically technological advances. The whole of semiconductor physics or semiconductor science and technology is based on quantum mechanics. Okay? So we are not studying a subject for the sake of it. We are studying a subject, we are looking at a subject which has got lots of practical, technical, technological applications we are all using in everyday life. How many of you are using smartphones? No, I will ask the question the other way around. How many of you are not using the smartphones? None. And what is a smartphone is consisting of? It's a small personal computer. What it is made of? integrated electronics. Integrated electronics is a result of quantum mechanics. So quantum mechanics is something which we all know about it, which we are using about it, and in the next 80 minutes, we shall see what it is, how it got developed. Okay? So I'm going to tell you a story. The story is long ago, so long ago, during the year 1900, there was a scientist by name Max Planck who thought completely differently to understand and explain a small experiment called black body radiation. Okay, the story starts like that. There are 4 fundamental experiments on which the quantum mechanics is built on. The 4 experiments are black body radiation, photoelectric effect, and then Young's double slit experiment and Compton effect. These 4 experiments laid the foundation for quantum mechanics. So the organization of this story is the following. I'll explain you what are these 4 experiments, and then the main question came, subatomic particles. Mainly it is on the subatomic particles. Do they behave like a wave or a matter, or what is called matter waves? Then we will go into the uncertainty principle. I mean, this is the sequence of the story. And then we will say what is probabilistic and what is deterministic attitudes in this quantum mechanics. And what exactly we do with quantum mechanics. What are the mathematics we do with that? With this mathematics, what we are trying to understand. And finally, I would like to tell you some interesting phenomena. One of the interesting phenomena in quantum mechanics, what is called tunneling. And finally, I would like to say, what is the real life applications of quantum mechanics? So this is the storyline. So I'm not keeping anything secret or suspense. You know the storyline. Now you may ask me, generally physics, we understand, first we imagine something, we will propose the theory, and then we would like to see the experiment. For example, if you say light scattering of light by the particles is first done by Rayleigh. Rayleigh is the name of a scientist. He studied scattering phenomena very thoroughly, and he proposed a theory, and a part of the theory could be done through the experiment. And they said, okay, theory works. The second part of the theory he predicted could not be done with an experiment till 1928, till Raman came into the picture. He has proven one experiment to prove that theory of light scattering. What I mean to say is, general understanding of physics is you imagine something, you do the experiment, and you try to make the story out of it. But quantum mechanics has developed altogether completely different fashion. It is dependent on 4 solid experiments. And these solid experiments has given something which is beautiful right from 1900. People could not imagine what's happening. So quantum mechanics started off in a very nice way with the experiment. And today, you are all talking about one application of quantum mechanics, that is what is called quantum computing. Okay? So what you study is only a part of what real quantum mechanics is. Fine? Now let's go into the story. The storyline is 4 experiments we would like to describe. Most of you know these experiments, but for the sake of continuity, let me explain the experiments. And during 1840 to 1890, the topics people were really working on is thermodynamics. If you see the evolution of Carnot cycle, diesel cycle, Rankine cycle, and the black body radiation, everything is connected with thermodynamics. That is also the era where automotive industry started growing up. because automotive industry frankly depends upon the thermodynamic cycles, and it is governed by the rule PV is equal to nRT. Simple rules. The black body radiation, they have done lots of experiments. You know what is a black body? A black body is a body which absorbs all the radiation falling on that and emits all the radiation from it. So a black body is something which absorbs all the radiation, emits all the radiation. So people started working the theory of it, how it is possible. You know, in 1840, 1850, the most important theories developed is electromagnetics, Maxwell's equations. Maxwell's equations mainly deals with electric and magnetic signals, and electric and magnetic signals are produced by oscillators. Oscillators, we are all familiar with LCR circuit, inductance, capacitance, and resistance circuits. So everything was dependent on oscillators. So in thermodynamics, to explain the black body radiation, people thought black body consists of an oscillator which will absorb all the radiations continuously and emit all the radiations continuously. Assumption was good. Based on that assumption, people started working out the theory. In the theory, what they observed is, in the ultraviolet region of the optical spectrum, that curve which is over here could not match, the theory could not match the experiment. Theory could not match the experiment at ultraviolet frequencies, ultraviolet wavelengths for the black body. They struggled hard, right from 1860, 1870, 1880. Many people worked on it, but they couldn't explain. 1890, it was Max Planck who thought why the oscillators should absorb the energy continuously. Why not in a discrete manner? Why not? This is one idea. Then he could work out the theory. It was fitting very well. By 1892, he is ready with the theory. It explains everything. And it explained everything with a simple formula. E is equal to h nu. Energy absorbed is equal to Planck's constant multiplied by the frequency of the oscillator, where the frequency is not continuous, it is discrete. When he said that, he himself was not convinced. It is a radical theory. Then he waited for 2-3 years. Then he published it in 1894. Once he published the paper, people started looking at it more critically. With his idea, what is his idea? The oscillators in the black body will not absorb the energy continuously. They have a selection of, they absorb it in particular packets, and the packet in German is called quanta. In, you say the English word quantity comes from the German word quanta. In fact, it's also the Italian word quanta. Okay, so quanta means a packet of energy. Then once he explained, people look at it. It explained very nicely. Before we go further, can you give me an example of a black body which you see every day? Can you give me an example of a black body you see every day? This question also to the online people, but online people cannot answer me. So I'm asking the people who are present here. Any, you see every day? No? I think your ragging is not allowed in this college. You know that? Don't rag me. The black body you see every day is the sun. Sun is a black body. Okay? So when this idea came, he proposed it and it was accepted. Once that is accepted, then came another experiment, photoelectric effect. Photoelectric effect is if you shine light on particular metals like magnesium, for example, they emit electrons. The magnesium metal emit electrons when a proper light is incident on the metal. Then Einstein immediately took the clue from Max Planck and he explained the behavior of photoelectric effect most convincingly. So photoelectric effect, right now we are describing the first experiment is black body radiation. The black body radiation clearly says it absorbs the light in packets, means some chunks, it's not continuous. Photoelectric effect also says the light is coming in terms of small quantities or quanta, and Einstein could explain this photoelectric effect. Incidentally, Einstein got his Nobel Prize for explaining photoelectric effect. He did not get the Nobel Prize for his theory of relativity. So after explaining this photoelectric effect, yeah, this is very important. Planck and Einstein were using the formula E is equal to h nu or hf. F happens to be the frequency. And frequency, whether you use f or nu, is equal to c by lambda. C is the velocity of light, lambda is the wavelength of the incident light. So that is the relation. So now what you have understood from these two experiments is black body radiation states it contains oscillators, black body contains oscillators, it will not accept the energy continuously, Max Planck. Because the light is coming in quanta, the magnesium surface is going to emit the electrons in packets. This is what was told by Einstein. So we are now more or less convinced that light is coming in terms of packets, quanta. So these are particles of energy. Then came a fantastic experiment, Young's double slit experiment. All of us have done the experiment in our in our college about the interference and diffraction of waves of light. This is to prove that light is having the phenomenon of waves. How did we get the wave nature? Right from Maxwell's equations. So light is a wave. If it is a wave, it should exhibit diffraction and interference. If any object is going to exhibit these two properties of diffraction and interference, that we call it as a wave. Okay, and a wave is always characterized by an amplitude. A wave will have an amplitude and it will have a phase. One is understood. And the wave also carries the energy. How it carries the energy? Now you know the Poynting vector S bar in our electromagnetic theory. S bar is equal to E bar cross H bar. The electric field vector with a cross product from the magnetic field vector will give you the energy, which we call it as the Poynting vector. So we know that a wave consists of amplitude, phase, and it carries energy. But now what is happening here? The same light which is behaving like a particle in the black body radiation and photoelectric effect is behaving like a wave. It's terrible. Then we go to the, this is the wave theory. So whoever is interested in knowing the optical beams, this is how we derive the interference and diffraction pattern in double slit experiment. In the double slit experiment, people are trying to ask a question. If I close one slit, there are two slits. If I close one slit, do I observe interference? The two slits are there in the Young's experiment. These are the two slits, slit 1 and slit 2 separated by a distance d. The light is passing through the slit and interacting on the screen. The two waves are interfering. When they are interfering, you are getting interference fringes. If you are having only one slit, do you get interference fringes? Or how do you distinguish between the interference fringes and diffraction fringes? If it is a single slit, you get diffraction. The difference between interference and diffraction is interference fringes are equally spaced and having equal intensity. They are equally dark and intense light, bright. Whereas in diffraction, the fringes are not equally spaced. The initial first fringe is going to be very bright, broad, and it is going to be very bright. When you go to the other fringes, it will, the intensity comes down. The fringe width also is going to change. Then somebody asked a question, I don't want to use light. I want to use a very dim light and I will start increasing the intensity. What do you mean by dim light? The number of photons traveling through the slit, I am controlling. If you put intense light, what do you mean by intensity? Intensity is the number of photons put together in a given area. If I start reducing them, do I still observe interference? These are the questions people have asked in the Young's double slit experiment. Why should they ask all these questions? Because the fundamental question is light a wave or a particle? Is light a wave or a particle? Already we have seen the particle behavior with reference to the black body radiation and photoelectric effect. The moment we came to the double slit experiment, the same light is behaving like a wave. If it is a wave, if I start reducing the intensity, means if I reduce the number of photons flowing through the two slits, do you still get a interference pattern? They observed something very interesting. They don't get an interference pattern up to certain point. After that, it is going to have an interference pattern. If you reduce the light, you get spots where you can really measure the number of photons. So what is that we are trying to understand now? Light behaves like a wave in the Young's double slit experiment as long as the intensity of the light is higher. If it is lower, it behaves like particles. Okay. Then they have done it with all subatomic particles like helium atoms, protons, electrons. They found they behave exactly like the wave patterns, giving the interference. I repeat my statement. People have done the Young's double slit experiment using particles. What type of particles? Electrons, protons, helium atoms, things like that. So you know you are shooting particles, but they are behaving like waves. So we are stuck with the question. Listen to the question carefully. When we are dealing with the subatomic particles and light, I would like to call it as photons, do they behave like particles as done in black body radiation and photoelectric effect, or do they behave like waves as we have seen in Young's double slit experiment and Compton effect? So this question remains whether the subatomic particles, what are subatomic particles? Electrons, protons, neutrons, muons, photons, all these things, which you can't see with your naked eye. So this Compton effect has very clearly shown that they will have a particle nature. So now we have, of the four experiments we have seen, two of them very clearly show the subatomic particles behave like particles. The other two experiments we have seen, the Young's double slit experiment and the Compton experiment, they behave like particles. I mean, in the Young's double slit, it behaves like waves, And even in the Young's double slit experiment, when you use the small photons, they behave like particles. Now comes the question, are the subatomic particles, are they waves or particles? Why are we struggling so much for this question? Because this same question we didn't have when we were dealing with Coulomb's law. You all remember Coulomb's law? We studied long ago, so long ago. What was Coulomb's law saying? Huh? Coulomb's law says, like charges repel, opposite charges attract. We know that. In the hydrogen atom, what is the nucleus consisting of? A proton. What is revolving around the nucleus? An electron. Why the electron comes and collides with the proton and everything goes boom? Proton is positively charged, electron is negatively charged. They should attract. Why don't they attract? Number two, if you take helium in any of these elements beyond hydrogen, the nucleus is consisting of protons of the same number as atomic number. So all the protons are together. What did Coulomb say? Like charges should repel. Why are they not repelling? Why the elements are so beautifully stable? What's happening? How do you answer these questions? Is the question clear? Subatomic particles in a system, they do not obey the classical laws, whatever we have studied. What is the classical laws we have studied? Coulomb's law with reference to charges. Okay, that is not applicable for subatomic particles. So, subatomic particles behave differently compared with the classical systems. Now, what is that we are trying to do? Is black body radiation, is it a classical or a quantum? Till 1890, it was classical. The moment Planck said the energy is going to be absorbed and emitted in packets, that became quantum. And Young's double slit experiment also said the same thing, and it said these particles need not behave as particles. They also have the wave nature. Okay, so now we can understand the subatomic particles, they behave both as waves and particles. If I say that, naturally you get a question, when do they behave like particles? When do they behave like waves? If you know that, at least you can know how to understand a subatomic particle system in the nature. One more question. Whatever is happening in the nature, for example, photosynthesis, if you go to the atomic level and molecular level, the electrons are changing and everything is happening with the electrons. Why up to that point? Take your own body. If you are touching a hot material, early morning you would like to have a hot cup of coffee. If you touch that cup, you feel it is hot. How are you feeling it is hot? The sensors are sending the signals to the brain through neurons by exchange of electrons from one neuron to the other, and the brain is getting the signal from the change of electrons, and you say it is hot. So if you see the natural systems in the nature, they are all quantum mechanical. They are not classical. Okay, so in order to explain the phenomena which are occurring in the nature, you must think in the quantum mechanical way rather than the classical way. If you do it in the classical way, you may not be able to explain as happened in the black body radiation. Am I clear? So just to give the important point, nature behaves in a quantum way. You can take the simple famous example of MRI. MRI, magnetic resonance imaging, is based on the fact quantization of electrons in the human cell. If the human cell is in the brain, if the brain is normal, the quantization rules are normal. If there is a tumor in the brain, the quantization rules are going to change. This change in the quantization rules we can find out by measuring the angular momentum of the electrons in the cell to a machine. Am I clear? So any phenomena you look in the nature behaves quantum mechanically. So if you want to solve the problems of the nature, you must think quantum. Classical, it may not be possible. We will come back to this point at the end of the lecture, where quantum computing can be useful. It's if you say quantum computing is useful to book my train tickets, probably we are wrong. I would like to say we are absolutely wrong. It's not. Okay. So with this, what is the question we are asking? How the particles, subatomic particles, do they behave? Do they behave like waves or particles? We have to find out. So subatomic particles and photons behave as particles and waves. Every wave has its own properties. Every particle has its own properties. Since we are familiar with the Newtonian mechanics, a mechanics proposed by Newton or even by Kepler, because these are all dealing with the big bodies, a particle should have a shape, a size, a mass. Okay? When it is moving with a velocity v, because it is having a mass m, mass multiplied by the velocity is the momentum, the particles must have a momentum. If it is moving with a velocity v, the particle possesses a kinetic energy which is equal to half mv square. So I can visualize a particle. If you want me to characterize a particle, I can specify its position, x, y, z in the Cartesian coordinates, or r theta phi in the spherical polar coordinates, or rho phi z in cylindrical coordinates. Or if you take any curvilinear coordinates, I can represent the position by u1, u2, u3. You can convert one coordinate to other coordinate. You are familiar with that. It must have, if it is moving with a velocity v, you must be able to characterize the momentum, and at a given time, where is the particle? You should be able to find out. That is the problem of physics. And if it is moving with a velocity v, it also must have an energy of mv square. We know that very well. If it is a wave should be characterized by a wavelength lambda. It must have a phase phi. So there is an amplitude and there is a phase factor for the wave. If the amplitudes are all together at the same phase, the amplitude, it is going to give you larger amount of energy. This is what we came to know through electromagnetics, Poynting vector E cross H. Okay, and the wave also has got a property called polarization. What is polarization? If you take electromagnetic theory, the orientation of the electric field vector with reference to the magnetic field vector, we call that as a phase of the wave. Okay, so therefore a wave has got certain properties, a particle has got certain properties, and the subatomic particles, photons, electrons, protons, and all these things are behaving both like particles and waves. If I simply say a wave, if you ask me what is the momentum of this wave, I should be able to tell you, because at some point it is a particle. So what is the problem I am facing now? I should have the combined properties of the wave and the particle. I should be able to give it to my subatomic particles. If I do that, I know that it is going to behave differently from the classical physics. What is the classical physics? Coulomb's law, Newton's laws of motion. These are the classical laws, including Kepler's laws. Remember, these classical mechanics can be worked out in different ways. For example, if there is a body, if I am pushing that body, I can push it with contact. This is called action at contact. But if there is a body like Earth and there is moon, the moon and the Earth are combined together with some force. This is what we call as a gravitational force. Are they touching with one another? No. This is called action at a contact. Action at a distance. So we have action at contact, action at distance. And what is all happening here in quantum mechanics is action at a distance. Action at a distance is characterized by fields. Electric field, magnetic field, gravitational field, nuclear fields also. Means they don't touch one another, but still they exert the forces on one another. Okay. So now the problem we have is you characterize the subatomic particles having both the properties of the wave and the particle. How to do that? This is a question I am asking you about 1912, 1915. These questions came. People don't know how to really go about it. If you don't know how to go about it, what do? Okay, I will have a formalism, I will have a theory. I can imagine that the wave is having both the properties of the waves and the particles. Because that is the only way out. Otherwise, how can you, because this is 2 points, you have to match them together. If the 2 points are independent, you are nowhere. You are unable to understand whether the particles are particles or particles are waves. Then came de Broglie. He is a French scientist. The spelling is very, take a precaution about the spelling. De Broglie, but G is silent, de Broglie. De Broglie said, I would like to call that as a matter wave. Every matter, every particle behaves like a wave and a particle. Then came the question, we asked the question, when it shows up as a particle, when it shows up as a wave. A system of waves, when they put together, when they superpose together, and when the amplitudes and the phase are in the same, amplitudes are superposed and phase is the same in all for all the waves, that shows the particle nature. I'll repeat. The wave, it's not a single wave. A matter is consisting of a packet of waves. This packet of waves means there will be different amplitudes and different phases for that packet. For example, you take an electron. I would like to give an example that electron is consisting of 5 waves. Let us say, if these 5 waves, each wave is characterized by its own amplitude, its own phase. If the amplitude are superposed in such a way that the phase of all these 5 waves are together, then you see a particle. If they are dispersed, if the phases are different, you see the wave nature of the same particle electron. Looks convincing, because what is the question you asked? If the particle behaves like a wave, tell me when it shows as a particle. I have given you the answer. When the amplitudes are superposed at the same phase, when all the waves are at the same phase, I'll see it as a particle. That he said in this fashion, and it is all the theory I have given. And I also asked one more question. If it is a particle, I have my momentum. Now show me the momentum for the wave, for which, I'm sorry, you may not be able to say this, lambda is equal to h by p. H is the Planck's constant. Where is the Planck's constant coming? Planck has given the formula, E is equal to, energy is equal to h multiplied by the frequency. What is that h? H is the Planck's constant. Planck's constant runs is a very, very small number, 10 to the power of minus 21 in proper units. So now I know the momentum of this wave, lambda. Wave is characterized by amplitude, phase, and wavelength. So if I know the wavelength, if I take h, the Planck's constant, divided by the momentum, I will get this relation, or P is equal to h by lambda. Since I know the wavelength, I know the momentum. So cleverly he has managed how to solve the problem of a particle properties for the wave. Okay, so for the wave, you got the wave momentum. A wave is having group velocity and phase velocity, and it carries the energy. At some point, when all the waves are going to be combined together in the same phase, you get your particle. So we got the answer that an electron, a particle, behaves like a wave and shows up all the properties of the particle and the wave together. With this explanation, all the 4 experiments we have seen, black body radiation, photoelectric effect, Young's double slit experiment, and Compton effect, 4 fundamental experiments of quantum mechanics can be explained. Okay, so this is called matter waves. Matter waves. So a matter wave is a concept proposed by de Broglie, which has solved all the problems of the wave nature and the particle nature. This I have explained. A wave packet is consisting of lot of waves, and you all know that a wave is always carrying the energy is called the group velocity and the phase velocity. A group of waves carrying or moving in terms of space and time will have phase velocity and group velocity. Phase velocity Vg is equal to omega by k. We know that from our intermediate physics. And group velocity is equal to d omega by dk. The moment I come into the waves, all the concepts of electromagnetic theory proposed by Maxwell will come over. What do you mean by Maxwell's equations? They must have the first order derivatives. They must have the second order derivatives. You should know how the wave is moving. If there is a wave, if you take the first order derivative, what is that you are trying to do? You are trying to find out the tangent of the propagation of the wave vector with reference to, at that point, what is the tangent or what is the slope of the wave? That's what we are talking about. So here I have explained how do you really look into the wave nature. For example, if I take a wave function, I'm just writing it down by psi. I can write by any other wave function. A wave function consisting of the amplitude A and a phase factor. The phase factor I can write down in terms of cosine function or a sine function or an exponential function. It matters, it doesn't matter at all. Because if I take an exponential function, e to the power of minus I theta plus e to the power of plus theta by 2 will give me sine theta. Similarly, I can derive cos theta, I can derive, if I use hyperbolic functions, I can derive tan hyperbolic. So therefore, I am completely comfortable whether I use trigonometric functions or if I use hyperbolic or if I use exponential functions, it doesn't matter. Only point that matters is the wave sustainable? Is the wave continuous? Is the wave progressive? Then I have to use a periodic function like a sine and cosine, which will make my mathematics much more simpler. It really doesn't depend upon the system. The system has its own properties. I can make my wave function applicable to the system. We are going to see that. So once you have this, most of you are also familiar with omega and t, time. Omega is the frequency. How do you get omega? E is equal to h nu, and omega is equal to 2 pi by lambda. And when you make an exponential should be dimensionless. So e to the power of minus I omega, you multiply it by the reciprocal of the dimension of omega with omega, so that it's going to be dimensionless. We call it as e to the power of minus omega t. I think you are all familiar with the Fourier transforms. Yes or no? Okay. Fine. If you are not familiar with, we will make you familiar with. For example, if you are seeing a system moving as a function of time t, a system moving with a function of time t. If I look in the time domain, means I'll have a watch and I watch it from t is equal to 1 second to t is equal to 2 seconds, how far it has gone, I can find out. Whereas if I use the my matter waves, if I convert that into omega, what is the change in frequency? What is the change in frequency? I come across in all the physics problems like light scattering. Then I would like to transform it from the time domain to the frequency domain. There you come across this Fourier transforms. So you can look into the evolution in the frequency domain. Sir, we don't understand all that. Can you be a little more specific? I would like to take the example of lambda and k. 2 pi by lambda is equal to k. Simple. And 2 pi by lambda, what are the units? Centimeters. So k must have the unit, k is the wave vector, must have the units of reciprocal of centimeters. How do you understand that? Because we are talking about space, x, y, z coordinates. How many of you are familiar with the photographs we have taken 10 years back with a film? It's not a digital camera. Our old ordinary cameras, do you remember how we used to take the pictures? There used to be a reel. We should load it on the camera, you shoot it, then take the roll to a shop to develop it. After developing it, you can see the picture. For example, you are taking a black and white roll. You shot the pictures, you took it to the laboratory, it got developed. Okay? Now, if you take the negative and see, how does your hair look like? Black? Huh? I'm a little deaf. If you take a negative and look at the negative, the hair you have shot, for example, you take not my photo, your photo, the hair looks white, but in reality, what is the color? Are you frightened to look at the negative? Oh, my hair is becoming black? No. The more the white you see, the more comfortable you are. What is the picture you are looking in the negative? Reciprocal picture. A picture which is opposite to what you think. Similarly, if lambda is the real picture, k is going to be the reciprocal picture you are going to look. So in the reciprocal picture, for example, if it is so vast, in the reciprocal space, it's going to be shrunk. Why the reciprocal space has come into the picture, we'll see it when we look at a little bit into the semiconductor science and technology at the end of this talk. So now we are talking about the wave, how it propagates in time and how it is propagating in space. Because a wave is having a coordinates of space and time. Am I clear? A wave is having its coordinates in space and time. How do you say it is space and time? For example, if psi, this is a function of x, y, z and time t, this x, y, z is absorbed in the amplitude. A is a function of x, y, z and t factor is over here, omega t. If there is a change in the phase, that also will go into the x and lambda, both are connected with the space coordinates. So what all I am trying to say is, I am trying to characterize my wave, which is representing a particle. Okay? I am trying to characterize a wave which is representing a particle. If I know the wave equation, I know the wavelength, I know the phase, I know the momentum, I know the energy. How do you know the momentum? Because it is defined in the previous slide. Here, P is equal to h by lambda. P is equal to h by lambda. Lambda I know because I know the wavelength of the wave. I know the wave momentum. So practically I have characterized both the wave and the particle together. So now I will take this wave function. Now if I say, if I am taking a wave function, what am I doing? I am characterizing a system which has got certain properties. Those properties I am plugging them into my wave. Okay. So if I know the wave function, what I mean to say, I know the system. For example, you take an electron and a proton. This is for the hydrogen atom. In the electron and the proton, what type of wave function you should take? One representing the electron, one representing the proton. Finally, what is your problem in quantum mechanics or in physics? Calculate the energy of the electron with reference to the proton. This is what your mechanics says. Your classical mechanics says, if a body is moving at a speed v meters per second, how much time it takes to reach that particular point. So I am manipulating with xyz coordinates and the time t for a particle which is moving. Here I am describing the wave function or a wave for a subatomic particle, how it is behaving. So I am characterizing the wave function. If I characterize the wave function, can I also characterize the particle? Yes. Particle location? Yes. Particle velocity? Yes. Particle momentum? Yes. So therefore, I am completely describing the system with a wave function. Am I clear? If that is done, maximum problem is solved. In classical physics, it's not. You must know the position, you must know the entire forces acting on the system. What is that we are trying to do? We are trying to understand the behavior of subatomic particles. Why should we understand subatomic particles? Because they are not behaving the classical way. How do you say? Classical way, an electron and a proton are together, they should get attracted according to Coulomb's law. In the hydrogen atom, there is a proton, there is an electron, they are not coming together. So nature is behaving differently with subatomic particles. So we are trying to understand how the subatomic particles are behaving. That behavior is called quantum behavior. Okay. So what is a quantum behavior? The behavior of the subatomic particles in nature, which cannot be explained by classical physics. Okay. Now, fine, you know the wave function. Next what? If you know the wave function, then apply the Schrödinger equation. Schrödinger equation is a mathematical representation to find the energy of the particle under given circumstances. Then you may ask me, sir, I have an electron. This electron with reference to this proton is stable as in hydrogen atom. I want to find out the energy of this electron. I'll repeat this statement. I have a hydrogen atom, I have a proton and I have an electron. This electron is stable. It's not moving here and there. It is only moving around the nucleus in the same energy, which means with reference to time, this system is time independent. As long as you don't disturb the system, it will have the same energy. If it has the same energy, now quantum mechanics is asking the question, calculate the energy of this electron which is bound to the proton in a hydrogen atom. How do you solve that problem? Is the problem clear? Same question I can ask you. If the electron in the neurons of your hand If they are not moving with reference to time t, they don't move. Find out the energy of the electron in the neuron. Neuron is a very big cell in which there are electrons. Find out the electron energy. If this energy is different, it carries certain message. Remember that. So as long as I don't touch the hot coffee, the energy of the electron is the same. The moment I touch the hot coffee, the energy of the electron is changing because I'm giving more energy. Now I have to find out how much energy it has changed. So finally, whatever you do in quantum mechanics, you are trying to find out the energy of the subatomic particles. Energy is one dynamical variable. You can also find out the momentum, you can find out the space, I mean the location, all these things you can find out. If you want to find out, just you have to write down the time independent Schrodinger equation if the subatomic particle is not changing with reference to time t. They are dynamical variables. What is H? H is called the Hamiltonian. Hamiltonian is defined as a total energy, T plus V. Sir, why are you complicating all that? In classical physics, we do everything by forces. If you know the force acting on a body, you can find out. Is it not? But even in classical physics, you cannot know the complete knowledge of all the forces acting on the system. For example, I am here, I have given some energy to my legs, I started moving. How much energy I have given, I can calculate. But if I want to move, put my leg over here, what is that which is preventing the leg to stand over there? Friction. If there is no friction, I can't walk. If there is zero friction, can I walk? Can I walk on the ice? Because the friction is very, very small. So, do you know the force exerted by the friction? We don't know. If you don't know, but still you are using friction for the motion, how are you? How can you calculate? You cannot. But if you go for the conservation of energy, is a universal truth. If I want to put this energy over here, the total energy of the system, if I can calculate, I can find out. So here, the Hamiltonian is nothing but the total energy. For a hydrogen atom, what is the total energy? The energy of the electron, the energy of the proton, and the potential between these two. That is the reason why I said H is equal to, or total energy is equal to T plus V. So I have to apply the Schrodinger equation in order to find out the energy. Now let us see the equation a little more carefully and then we'll proceed. If you see the left hand side of the equation, H multiplied by psi. H is the Hamiltonian. Hamiltonian is an operator. Those who are doing with mathematics, they will come to know. We use operators in mathematics. If you, for example, you want to multiply 2 multiplied by 7. If you take a mathematical calculator, you give the input 2, you give the input 7, and then you give the input what is the operator. Operator is a multiplication, 2 into. So here, H is an energy operator. If you operate it on the wave function, what is the wave function? Wave function is the system which you have the complete knowledge about it and you are writing down the wave function. So H is operating on the wave function side will give you the energy of that particular subatomic particle. If the subatomic particle is not changing with reference to time t. Now you may ask me, if it is changing with time t, what am I going to do? You have to apply time dependent Schrodinger equation. Time dependent Schrodinger equation is I dou psi by dou t is equal to H psi. The moment dou psi by dou t comes into the picture, the system is evolving as a function of time t. Sir, can you give an example for a system which is evolving with reference to time t? Simple example I will give you is the Brownian motion. I may talk technical, but if you take a drop of ink or 1 particle of potassium permanganate and put it in a beaker of water, you know what will happen? If you put a drop of ink in a beaker of water, is it going to go zoom and then all the water will get into blue color? No, it goes very slowly. So if you take 1 particle of the ink or 1 small particle of potassium permanganate, it evolves as a function of time t, changing in its energy. How do you calculate this problem in the quantum mechanical way? Apply time dependent Schrodinger equation. So the first question is, I'm summarizing it, we'll go further. Any subatomic particle can be explained by a wave function. Yes. If you want to know the energy of the subatomic particle or any dynamical variable, apply the operator on the wave function. If you want to know the energy, that is called the Hamiltonian operator. H psi is equal to E psi is the simplest of all the equations. It is called the Schrodinger equation to find out the energy. Hey, why am I telling all these things to you? Why am I telling all these things to you? Because in your quantum computing, you will come across what is called a qubit. A qubit is one which is similar to a classical bit. What is a classical bit? 0 and 1. What is 0 and 1? Anybody? You're all, I think, computer science specialists. What is 0 and 1? Fantastic. Can you measure it? Can you measure zeros and ones? How does a computer really says it is 0, it is 1? 0 and 1 are the actual passage of current through the logic gate. If the output of the logic gate is not there, you designated that as 0. If there is an output from the logic gate, you are designating that as 1. So what is that you are actually measuring? The current passing through the logic gate. That's a measurement. Okay. So if this measurement is 0, in your nomenclature 0 means in my hardware, that is the current is passing through the logic gate is 1. Clear? So what is that you are trying to do? You are trying to make a measurement for a bit, 0 or 1. Similarly, you have to make a measurement of a qubit. A qubit, what is that you are trying to measure? A defect level with reference to energy or the spin of an electron. How does the spin of an electron can be measured? Through electron spin resonance measurement. Anything I say in terms of bit, that should be measurable. Without measurement, nothing can be done. Okay. So when you are measuring the energy of this electron by some technique, you have to calculate it with the Schrodinger equation. Okay. So the Schrodinger equation is going to give you actual measurement of what is going on inside the logic gates. Okay. So now we have seen the energy of the subatomic particle can be measured if it is stationary through the time independent Schrodinger equation. H psi is equal to E psi. If the subatomic particle is dependent on time in its energy evolution, you have to use time dependent Schrodinger equation. As I told you, we invoke operator algebra, but you are so nice, you didn't ask me the other questions. If there is a particle, you should be able to characterize where it is. The location should be done. The momentum should be known. The energy should be known. The potential should be known. All these things we use operators. These are the operators: position, momentum, kinetic energy, potential energy, total energy, and angular momentum. These are the ones we are trying to measure. These are the parameters you are using in your qubits. So therefore, this is important for you. to find out theoretically how much is the parameter, these are the dynamical variables you are measuring, and how much you are going to calculate. Now, I have done about the physical system. Madam, how much time I have? 5 minutes. We started at 4:30, no? No. Anyway, I'll take about 15 minutes. Bear with me, okay? Because I can't close it down abruptly. What I mean to say is, you said wave function is my photograph of the subatomic particle. Wave function. If I know the wave function, if you ask mathematics people, so there is here, he will tell you thousands of wave functions. Can I take all those thousands to represent my particle? No, I cannot. I cannot live with it. And I have only wave function and I have some mathematics. I must follow certain rules. If I know this gentleman, I can trust him when I'm giving some money to him. The trust is there. How do you trust him? You ask a few questions. Until and unless the trust is established, you don't want to do anything. How the trust is established? Or ask the question, you know the wave function, you know the operators, how do you get the dynamical variables I want for the system? You have to follow certain postulates, certain rules of the game. The rules of the game is, what are the characters for the wave function? Wave function should be, here I'm just summarizing them. This is, I would like to call it as state and wave functions. I cannot take all wave functions, whatever I feel like. The wave function where all the amplitudes and the phases are together, I should see my particle. This is what we said. All those rules, I'm going to give it over here. The wave function and its first derivative should be continuous, single value and continuous. So I have certain rules for trusting the wave function, to represent for a physical system. Why should I tell you all this? Tomorrow, you are going to listen to a word called collapse of the wave function. What do you mean by collapse? Wave functions do not collapse by themselves. What is this wave function representing? With an operator, they will represent a dynamical variable. That dynamical variable you should be able to measure. Without measurement, there is no qubit. When you measure, the condition of measurement, they will say the wave function is collapsed. What do you mean by that? After you make the measurement, the wave function does not represent the original state of this electron. Why is that? Because when you want to measure, you have to tap that system. How do I trust this man? I must ask his name. I should take his Aadhaar card. Then only I can trust him. So you are tapping that system for its properties. Once you tap, you know everything, then you can trust. This is called the relation between wave function, collapse of the wave function, and the postulates. Postulates are nothing but a set of guidelines for you to calculate the dynamical parameters of the subatomic particle. Am I clear? So I'll not go into the details of it. I will leave the PPT with you. You can go through that. I have postulate 2. This is related to the operator algebra. If I operate my wave function with the Hamiltonian, Hamiltonian is the total energy. What do I get on the right hand side? The energy. If I operate the wave function with a momentum operator, what do I get on the right hand side? Momentum of the system. Okay. And postulate 3 is, I am using operators. What type of operators are you going to use? These operators must have a specificity of Hermitian operators. It's not a big deal. Hermitian operators give you real variables. I cannot say, I cannot measure it, but I can tell you, no. Whatever you can measure, you should be able to operate corresponding operator. Then automatically, all the operators are Hermitian. Because this is mathematics, how do you check whether an operator is Hermitian or not? I have given you the rule. Okay? Okay. then wave function should be normalized. What do you mean by normalized? I told you wave functions can expand in a large position coordinates. You can combine them to a small, which we have done it with the k vector, which is the reciprocal of the wavelength. So therefore, I'm going to normalize the wave function for my convenience. It need not be a big stuff. So therefore, I'm also giving you what is the time dependent or time, the system is evolution as a time t. Use time dependent Schrodinger equation. If it is stationary, make use of time independent Schrodinger equation. Okay. Fine. Here comes, I will concentrate on two topics and then I'll stop it. The momentum and the position. You know, position is x, momentum is mass into velocity. You cannot measure the position and the momentum simultaneously. This looks very funny, but this is what happens. How do you measure a system? If I want to measure it, I have to touch it. I have to disturb it for any measurement. You know, measurement is in mathematical terms, excitation and response are linear or maybe non-linear. You must have an excitation, look at the response of the system. So therefore, this is given by Heisenberg in 1922. It was his PhD thesis. Do you have any question? And we talk, and the result of this uncertainty principle is tremendous in quantum mechanics, and the technological advancement, application of this uncertainty relation is your scanning electron microscope. Scanning electron microscope is based on this principle of uncertainty. Okay. Now, more or less, this is the last part of it. Suppose if I ask you, I close all the doors, I ask you to get out from this room. Can you? You cannot. Because physically it is impossible for you to break the wall and go. For example, there is a single wall. Can you jump over the wall? Your energy is not sufficient. So classically, you cannot go over the wall if you are a particle. But if it is a wave has got a probability, some finite probability on the other side of the wall. So a subatomic particle, listen to me very carefully, a subatomic particle, even though it has lower energy than the barrier, it can pass through. Sir, you are doing some mischief. How can it be, sir? Is it possible at all? Now I'll ask you, any ECE faculty are here? Everyone is computer science, you are ECE. Do you know the tunnel diodes? There are components called tunnel diodes. A diode is an electronic component. It will pass current only in one direction. But a tunnel diode, a part of it also goes on to the other side. Even though the barrier is very big, because of quantum mechanics, there is a tunnel diode. And tunnel diode, he can tell you, is a practical device we are using in our electronics. So tunneling phenomena is something, those who have seen the Harry Potter tunnels through platform number 12.5. Do you remember that episode? He just tunnels through. That concept is taken from quantum mechanics. This concept is so important, it has revolutionized the entire electronics to some extent. So tunneling is, finally, this is all about tunnel diodes. We will end up this talk with a cat. Imagine there is a box. All of you know about it. In this box, I have put some poison, also put some milk, fresh milk, and I put a cat. I close the box. After one day, I would like to ask you, I will try to open the box. What will be the state of the cat? Is it alive or is it dead? Because if it takes poison, it's going to die. If it drinks milk, it may be alive. So what do you want to say? Is it alive or cat? Is it alive or dead? Classically, I don't want answers. You are a cow. You know a cow? Cat on the wall. You can say anything and it will be right. And you wanted to say it's alive and dead. See, this is a most important logic quantum mechanics only can give you. So if it is classical, either the cat is alive or dead. But quantum mechanically, it can be half dead, it can be half alive. You can take any probability you feel like. For example, if I toss a coin, what is the probability it's going to be? Neither tails nor heads. Will it be there? It will be there. For example, if the coin is standing after I toss, will this probability be accounted in classical physics? No. But in quantum physics, that is possible. So this Schrodinger cat can be dead, can be alive, can be half dead, can be dead to 10%, 20%. This is most important for you when you are arriving at a most probable calculation of a decisive result, which is not available in classical mechanics. Now, I may give you a small example and then, yeah. For example, if you are making a drug design consists of about some 15 molecules, let us say. These 15 molecules, you have to calculate in such a sort of iterative way. Classical computers may not be able to give you. Quantum computers will give you, but they will give you all possibilities. So you should have the boundary conditions to choose which possibility is better suited for you, optimize it. That is the reason why optimization is most important in this data collection. And yeah, this is going to be my last slide. Classical physics is deterministic. Quantum physics is probabilistic. This is the main difference between the two. Why we said probability? Because you can find the particle when the amplitudes are together or superposed positively and the phases combine positively. This is a probability. This is not deterministic. You may say there may be a particle, maybe, but that maybe can be 96%. Okay, this is the most important logic all the quantum computers use. With this, I'd like to say we have seen this. I thank you very much for your time. Yeah, I'm almost done. I hope there are no questions. If there are questions, ask me later. I'll try to answer.
It's my privilege
Job done.
to propose both of hands. I sincerely thank Dr. Subramanian Garu for delivering such an informative and inspiring session on quantum mechanics. Your explanation of the concepts